So, thank you very much for the invitation to speak to you today. I'm very sorry I can't speak in German. I could do it in French, but probably English is easier for the majority of people here. So I'm a materials scientist working at EPFL in Lausanne, and the work of our laboratory is devoted to improving cement and concrete so that it has lower CO2 emissions, and we seem to have a problem on making this work. Okay? Yeah, that's what I'm doing. Okay. Whoops. Well, we need to go back a bit, but oh dear, what's happening here? Okay. So I've called this talk Future of Cement and Concrete, and I think we're hearing more and more about cement and concrete, how much CO2 it emits. So I think it's kind of useful to start with a little quiz, except it doesn't work because it's meant to be animated and you're not meant to see the answers, but never mind. So you see here I've compared various different sectors, cement and concrete, iron and steel, clothing, maybe a big surprise that, passenger transport, road, food loss, food waste. And the message here is, yes, cement and concrete is making a lot of CO2, and we need to improve that, but there are a lot of other things that are emitting the same kind of amount of CO2, so we need to really work on everything. Now, the reason we have these very high emissions from cement and concrete is that we produce so much of it. So we produce more materials based on cement than we do of all other materials put together. And in fact, as you see at the top here, it's intrinsically, in fact, a low energy material with low embodied CO2 and embodied energy. So we don't really improve things by replacing concrete with other materials, but we couldn't do that at any rate because, timber is a very good material for construction, but if we wanted to replace just 1/4 of materials made from cement with timber, we would actually have to plant new forest 1.5 times the size of India. And I think we can easily realize that this is just not feasible given the competition for land use. Most of what I'm going to say, I don't know what's happened to these slides because they seem to be in a completely weirdo format and they don't move. Okay, so if you want to know more about what I'm going to say today, please download our report we wrote for UN Environment a few years ago. Okay, so cement is kind of unusual in that most of the CO2 emissions are not coming from the energy. And this is important because even though we can move to renewable energies, it's a little bit more difficult for cement. That's not really going to solve the problem. And cement kiln looks like a kind of dirty industrial tool, but there's been immense improvements in the efficiency in the last few decades. And now it's actually one of the most efficient high-temperature processes there is. And furthermore, it can be really effective to use in terms of waste disposal, because in Europe, many factories, including those in Switzerland, are operating with more than 80% of waste fuels, which of course really reduces the need for fossil fuels. So most of the emissions are coming from limestone. Limestone is 80% of the raw material, and during the process it breaks down into calcium oxide and CO2. And I'm going to come back to that because of course then a lot of people say, well, can we replace limestone? And we'll see the answer to that in a minute. In terms of where concrete's being used, we have to realize that only about 10% is being used in developed countries. Only 5% in Europe, and the amount used in Switzerland is really very tiny. Therefore, if we're going to address the problem of cement and concrete, we have to engage with what's going on in emerging and developing countries. And we've seen tremendous growth in China in the past 3 decades. China's probably peaked now. The demand for cement is going down, but this is now going to be replaced by demand from India and particularly Africa. I mean, in India today, the consumption of cement per person is about 5 times lower than in China. And of course, in these countries like India and other countries, and that means that in these countries, the relative impact of the CO2 is much, much higher. So you see in the United States, the impact of cement and concrete on their CO2 emissions is really tiny. It's only 2 to 3%, whereas in a country like Vietnam, it's 25%. And of course, in these countries, we have a very large need for housing for people. Oh dear, now we don't, so it's not working again. Okay, so you see that many people are living in really, really unsanitary housing conditions. Of course, this leads to a lot of disease, and the very unsatisfactory living conditions, of course, give a big incentive to people to try to migrate. So if we want to solve this problem, we really have to be able to provide them with decent housing. And the figure on the right shows first of all, the real figures, but then the projections for the increase in the demand in the population, and therefore demand for cement that's occurring, for example, in the West African region. Whoa. It's very bizarre. So, yeah, I have all nice animations on all of these slides, but none of this is working. But let's worry about that. So, the important thing to realize is there's really no magic solution for doing away with the CO2 emissions from cement. Many manufacturers are saying, well, we have to go for carbon capture and storage. And I think we know that this is really not a realistic solution because it's going to be extremely expensive and very difficult to implement. On the other hand, we can actually make very, very large reductions if we work at all the different levels. So I'm going to speak a little bit more about how we can reduce the clinker in cement by using substitute materials, but we also need to work on the levels of reducing cement in concrete, reducing the concrete in the buildings, which is of course where you architects come in, and more efficiently using and, of course, reusing buildings rather than demolishing them. And if we have to demolish them, then we have to make sure we can recycle. And, of course, concrete can very well be recycled on many different levels. You can take elements and you can put them into new buildings, or you can crush them up and put them back in concrete, or you can use the fine material and use it to make new cement. So there's many, many different levels you can recycle on. Now, as I said earlier, more than 60% of the emissions are coming from limestone. And the question is, can we do something different? Well, the short answer is no, if these slides are going to move for me, because we have the composition of the Earth, and the composition of the Earth is such that more than 98% is made of just 8 elements shown here: oxygen, silicon, aluminium, iron, calcium, sodium, potassium, magnesium. And if we think how a cement works, so very simple scheme of how a cement works is like this, that at the beginning we have these gray powder floating around in water, and this is very nice because it makes the material fluid. We can place it in the forms, and then what in fact happens is the cement starts to dissolve. Like if you put sugar in your coffee, it will dissolve. It will dissolve and start to go into the water, but then the different elements that make up the cement, they get into new combinations, and what happens is they can deposit these new materials, which are called hydrates, and here I'm showing them in red. And because these are then combining the water, it's actually a chemical reaction with the water, it occupies a higher volume and it sticks all the grains together. Now, if we want those properties of being able to dissolve and then deposit these new hydrates, what we find is that when we look at these elements that are very abundant, we find that the sodium and potassium, those are too soluble. The iron and magnesium, on the other hand, are too insoluble. So we come to a system of just 3 oxides. So this is kind of amazing because, we've taken the whole composition of the Earth and we end up finding that there's only sort of basically 3 elements with oxygen that we can use. And of course, this means that we can really explore all the options. There's no surprise out there. And this system, of course, has been studied for well over 100 years. And we find, as I hope I might show you in the next slide sometime, that there are really just 2 regions where we can have cementitious materials. There's this region on the left, which we call Portland cement, which is basically calcium silicates, and the region on the right, where we have other compounds. These do have lower CO2, but the problem is we can't really make much of them because we'd have to use bauxite, which is available in short supply. I don't know why this is really so problematic. Oh, okay, so, yeah. So, I think this is important because when you read the studies that many people have done in their roadmap, they come up with the solutions that are possible, and then there's this big gap between what's possible and what we need to do. And they say, well, this is going to be breakthroughs. There's going to be some breakthrough in the future. But what I want to convince you about is that really there is going to be no breakthrough because of this composition of the Earth, which clearly is not going to change. And the fact that, cement is a solid material, we can't miniaturize it. People can't live in nano houses or virtual houses. And there's unfortunately a lot of people out there who are, saying a lot of really things that aren't true about what can be done to make cement with lower CO2. And one of the things people are saying, they're not really understanding the process. So the process, as I've explained to you, we start with limestone. This gives off CO2 during the production, and then in fact it can reabsorb that CO2 over its lifetime. The problem is that's not a solution because the reabsorption occurs much, much more slowly over 100 years or so. But what, of course, some people say, they say that what we can do is we can add things like calcium oxide to cement, and then it will absorb more CO2. Well, this is kind of true, but it's actually no help because they don't really take account of where you get the calcium oxide from. In getting the calcium oxide, you give off a lot of CO2, and you can't gain back more than you gave out in the first place. And similarly, there's a lot of sort of romantic notions that we can use algae and bacteria to form calcium carbonate, and they do form calcium carbonate, but the problem is they also need calcium to do that. So you have to give them a source of calcium, and only if this was uncarbonated, and we have hardly any of that around, does it have any net benefit. So the next slide is another technology, but I'm going to skip over that if I can make it change because we're running out of time here. But the message is that Portland cements will dominate. And what we can do is we can replace a large part of the Portland cement with other materials. And in the past few decades, what we've done is to use byproducts of other industries. Particularly, we've used fly ash, which comes from burning coal, and slag from producing steel. And both of these can be substituted in cement. But the problem is, if the next slide ever comes, is that the amounts of this fly ash and slag are available in quite small amounts. And therefore, the level of substitution can't go up more than what it is today. And moreover, of course, things like fly ash are probably going to disappear because this comes from the CO2-intensive process of burning coal. So we have to look at what else we can have available, and basically this is where we come to the idea of calcined clay, which is what we're really working on in our lab. Because clay is super abundant. If it's calcined, that's to say heated to a modest temperature of about 800 degrees, it becomes a very reactive material, and then you can use a combination of calcined clay with limestone to give you high levels of substitution. So here on the next slide, you will see that for a material where you have 50% less clinker, you can really get the same strength evolution, but you have 40% less CO2, which of course is then very interesting. And some properties are even much improved, like particularly resistance to chloride, which is the #1 cause of poor durability in concrete because it corrodes your reinforcing steel. And the kind of clays we need are really very, very widely abundant. So everywhere you see this kind of orangey, this browny orangey color, then you have the suitable clays you need. So you see these are actually available in those countries where the demand is really going up, notably Africa, South America, and Southeast Asia. So this is really a viable solution because we have these materials available. And often even these materials are byproducts from other mining operations, like that you saw very quickly. Oh dear, sorry. Oh dear. So if you can really roll out this technology, and it is very, very easy because you can apply it with existing technology, we have a potential to save 400 million tons of CO2 per year. And that's a really important figure. Just to put it in perspective, it's like 10 times the emissions of the whole of Switzerland. So we know how very difficult it will be to go to total carbon neutrality in Switzerland. Of course, we should do it. But if we invest in this technology, we can have 10 times more impact. And of course, CO2 doesn't stay within national boundaries. And we can produce this, as I said, with existing equipment available today. I really don't understand this slide controller. And this shows you, for example, a full-scale house we built in India. In the next picture, there's another application. Oh. And where? Here. Okay, well, I'm pointing everywhere, but it's just impossible. So, okay, and finally, at the end of the day, we can do this even more cheaply than we do it today. So fortunately, after quite a few years of promoting this technology with the support of the Swiss government, we are getting really traction in the area, and the major producers are really looking to produce it. This just shows a few of the extracts. Oh, come on. No, that's not the one I want. No, why are we going forward? I want to go back. Oh, dear. Right. Okay, so maybe I stand over here, it works. No, it doesn't work any better. I think it's supposed to be running out of battery, quite honestly, because it just doesn't work. Okay, this was just showing you how this technology really is being taken up by the big players. Quotes from the strategy of Lafarge-Holcim, from Heidelberg Cement, and from the International Energy Authority, all really citing this as the technology that can help to reach lower CO2 emissions. I just want to come back to my previous slide here to say, as I said at the beginning, that this is not the end of the story, because we still need to work all through the value chain. And just to give you a quick example on this, if you look at these figures for concrete, the important thing is to see the scatter. because what this tells you is that for a concrete with exactly the same performance, you can have some concretes that use, 1 unit of cement and some which use 4 times that amount. And clearly, if you're using 4 times that amount, then you're wasting 75% of this, you're increasing your CO2 emissions by 4 times. And this is what we have to stop doing. So finally, I'm at the end. I'm sorry for all the technical issues, and it's not normally how I present, but at the end, I really want to give you 3 messages. First of all, please, I think people need to stop demonizing concrete. We can't replace it in any significant way, and we really need it if we're going to solve the problems of growing populations and urbanization in many parts of the world. The second message is don't expect miracles. There's no kind of magic wand out there that's suddenly going to produce an alternative to concrete. So please be careful what you read in the press. You can't have completely zero carbon concrete. You can't have carbon negative concrete, but you can have very low carbon concrete. And to get this very low carbon concrete, you need to work at all the different levels. What I say, join the dots. You really need to optimize at all levels. So you need to optimize at the level of the cement, at the level of the concrete, and the level of the buildings. And therefore, we really need to promote the dialogue between the material scientists, between the civil engineers, and between the architects to achieve those reductions, which are possible. And, I think in that way we can really have a very huge impact worldwide. So I'd like to thank you for attention and sorry for all the difficulties.